Hello, everyone. Welcome. Thanks for joining our diagnostic training session today. Now, this is a pre-recorded session this week as I am traveling. So if you do have any questions on Zoom, just feel free to reply to the confirmation email that you got when you signed up for the class. If you're watching on YouTube, feel free to leave a comment. And on Facebook, leave a comment as well. And I'll get back to those when I return. So my name is Jason Gabrinas. I'm one of Snap-on's National Diagnostic Technical Trainers. Been in the training department the last 13 years or so, traveling around North America, helping techs and shop owners get the most out of their diagnostic equipment. Before I did that, I was a couple years as a diagnostic sales rep at Snap-on, so I had about 30 different franchisees I worked with, as well as the shops that they service, in order to help everyone get the most out of their diagnostic needs. And before I did that, it was 8 years at Subaru, so worked in a dealership, and I guess just over time became that default diag guy in the shop. So I always ended up with the drivability problems, the intermittent problems, the weird wiring problems that would show up on those cars. And that's really where I cut my diagnostic teeth, was trying to figure out all those weird head scratcher type cars that would come to my bay. And before that, a bunch of other miscellaneous wrenching jobs. Been about 30 years under hood experience for me. So our topic today is back to basics. So we got to think about, as you're going along and you're diagnosing a vehicle, especially maybe a drivability issue, something or something particularly tricky. Sometimes we forget things. Sometimes we forget just the basic stuff about how a car runs, and maybe eventually, it comes back in. Oh yeah, why didn't I check that? Things of that nature. So let's focus on the basics. What makes an engine run, right? And what should we test? And a few tests that we can do in order to cover those basic items as we go forward. Now, one good way to do this would be to have a repeatable workflow. That way we don't necessarily forget the basics, right? So the workflow all the way through is going to be, first step, we're going to intake the customer. We're going to make sure we understand what their complaint is. Is it a drivability issue? Is it an engine light? Is it a vibration, noise? Whatever it happens to be, go through and capture that customer's complaint. Then we would want to road test the vehicle to verify what the customer's complaint is, and then inspect the vehicle, uncover causes, uncover maybe other issues that might be on the vehicle or other related issues that the customer might not be aware of. Then we want, of course, pre-scan as well while we're doing all this. We want to check all systems for codes just to see, is there a code or not? Sometimes there isn't, but then we proceed from there. Depending on what the results of the scan are, we would proceed with our diagnosis, of course, and then repair the problem. And then most likely, especially nowadays, we have to do a lot of resets, relearns, recalibrations, that sort of thing. So we reset the system, road test the vehicle again, and then verify that everything is complete, and then do a post scan to give it a clean bill of health. So as far as defining the problem, a good way to do this is using something like a drivability worksheet. Now, there's a multitude of these. If you have Shopkey or Mitchell, we have a bunch of those right in the product, readily available. Also, shop management system, or a lot of folks do digital vehicle inspections. That's a good way to go through and just check the boxes, make sure we're not missing anything. What kind of a problem is it? Is it a drivability problem, a no start, a noise, a drivetrain problem, an electrical problem? Use that customer interview worksheet. And then, of course, the road test and a pre-scan, right? So the pre-scan is going to be, of course, tell us whether or not there are any codes. Now, there might not very well be any codes on the vehicle, but depending on whether or not they come back is going to dictate which way we go. Now, if it is a drivability problem, it's going to depend on the problem. If it's a drivability problem and no codes, we're going to check TSBs. We're going to check maybe SureTrack, which would be our experience-based information database. And remember the basics of combustion. This is going to be the main focus here, is fuel, air, spark, and compression. Make sure we have all of those and make sure they're all correct. Check the fuel trims, check the fuel pump, check the injectors, check the ignition, check mechanical, depending on what it might happen to be. So all of those things, we need to make sure that the vehicle is working properly in order to diagnose one of those drivability problems. So first off, let's try with TSBs. So a good example here, we got a 2012 BMW, and we're going to check, look up engine runs rough on Shopkey. We have running rough right there. And if we look under the TSBs, we will see there's a couple under engine. And first one says engine misfire due to a failed ignition coil. Well, yeah, that could very well be a problem. But the interesting thing about this is, if we go through this, the current ISTA misfire test plan for these engines can be lengthy to complete and does not provide an effective method to diagnose a faulty secondary ignition component. So even BMW admits when they're wrong sometimes, right? So it takes a long time and it might not necessarily get you the result you're looking for. So it goes through a few different things, but basically it boils down to these came with originally Bosch coils, and then they ended up doing a running change to replace them with these Delphi coils over here. So this bulletin basically says if you find a Bosch coil, replace it with a Delphi coil, and that should solve the problem, right? But TSB, right from a TSB. If I hadn't checked that TSB right away, I might have fought doing a bunch of other things, checking fuel and checking all this other stuff. When in reality, they were just faulty ignition coils from the factory. So, uh, one good example as to why we would want to check our TSBs. SureTrack. So this is our experience-based database that we have. So we have, TSBs were there. We also have information for real fixes. So that would be top fixes based on count. How many times was that a confirmed thing? And we see right here, number one there, replace ignition coil, makes sense due to that TSB, right? It could be things like coil and plugs, engine runs rough, adding that in there, engine run rough on acceleration. So different variables. Next one's top repairs. This is based on real world repairs, billions of real world repairs. What have other techs done in this space? So replace ignition coil number one, of course, plugs, valve covers, that sort of thing. Next one's going to be causes and fixes. So that's called ProView. And what that does is it takes that information that we had on the top repairs and you can do combinations with this. So runs rough could be these. Idles rough could be something else. Runs rough while accelerating, that narrows it down a little more, right? We can do it by symptom. Or if we had a code, we could do it by code as well. So runs rough while accelerating, narrows it down to spark plug and ignition coil in that case, right? So we can see the ranked fixes. And sometimes it's not as straightforward as this. Sometimes it's something a little off the wall that you might never have thought of, but it actually ends up fixing the car. So next one, if it's a drivability problem, one of the things we need to worry about is fuel, right? So fuel trim. Fuel trim is often misunderstood, I've found. It's a window that allows you to see what the computer is doing to control fuel delivery and determine how the PCM's adaptive strategy is operating. So basically, when we have the engine running, we want to keep it at that 14.7 to 1, the stoichiometric air-fuel ratio. So going to drive down the road, and the front oxygen sensor is going to see, oh, I'm lean. So in the case that it's lean, it's going to call for a positive fuel trim. So you'd see a positive fuel trim number on the scan tool. Then it's going to add fuel. And then eventually, it's going to say, oh, now we're rich. So now that we're rich, we got to do a negative fuel trim. We got to pull fuel away. So we're going to negative fuel trim number or a smaller number, positive number. To pull the fuel trims back. And then all of a sudden, oh, now we're lean. Go to a positive. Now we're rich. Go to a negative and so on and so forth. It's just a continuous loop. That's why they call it closed loop operation, right? It just kind of goes in this loop, rich to lean, cycles back and forth. Also, our fuel trim feeds into, or our oxygen sensor feeds into our short-term fuel trim and long-term fuel trim. We talked about that with the oxygen sensor there. I'm reading lean, now I need a positive fuel trim. So it goes into short-term fuel trim. Short-term fuel trim is going to be right then and there as it's happening. So that kind of as it goes up and down. But if we have a consistently high short-term fuel trim, for example, that would feed into long-term fuel trim, and the long-term fuel trim would start going up as well. It takes longer to build into the long-term fuel trim, but that's basically how it works. So the sensor tells rich or lean. Short-term fuel trim is going to tell us what's going on right now. Long-term fuel trim is going to tell us what's been going on over time. So let's look at some data and see how this would look in a real exercise, right? So create a vacuum leak, look at the oxygen sensors in relationship and comparison to fuel trim, then repair the vacuum leak and see what happened. So right here we have just running. Now in this one it has a air-fuel ratio sensor in the front and a zirconia sensor in the back. So that's kind of how it's going. That's kind of how it's going. So one is good for the AF sensor. And we'll see that it's barely correcting the fuel. So this is on a Subaru. So on a Subaru, short-term fuel trim is called air fuel correction, and long-term fuel trim is called air fuel learning. So we see it's pretty low, 0, 1, 2. It's right in there. And then as we create the vacuum leak, we can see the fuel trims go up considerably. And we can also see the AF sensor reacts with the lean condition. So up on an AF sensor is lean, down on a zirconia sensor is lean. So we can see they go away lean. and then it goes positive 35 right there. Let me go a little further. So starting to do that. Long-term fuel trim builds up. Then I go to my max here. Notice how it lags. So the long-term fuel trim was still going up even after I repaired the problem. Once I repaired the problem, everybody went rich, like full rich, because it was asking for fuel and asking for fuel and asking for fuel, and all of a sudden that vacuum leak goes away. Then it's still asking for fuel for at least a few more milliseconds. So we're going to have excess fuel in there, and then you can see it adjusts as we go. It kind of goes negative right there, real quick, and we can see where it goes full rich, and then really quickly it redevelops and adjusts itself back to where it should be. So we can use our long-term and short-term fuel trims. More long-term fuel trim to see if we got a big problem, but short-term fuel trim in the short term. If I have this problem right now, or have I had this problem for a long time? So if you're plus or minus 5% on your fuel trims, short-term or long-term, you're doing okay. Yellow light, going to start worrying about it a little bit. Maybe there's something it's correcting for, some sort of a maintenance issue or something like that. Plus or minus 6 and plus or minus 19%, and then anything over 20% either way is going to set a code more than likely. And really what we were taught in Subaru school is if you see anything in double digits, it's probably a problem. Right? So that's our fuel trims. Now let's go to checking components, right? Fuel system components. So when we're checking components, testing them, we can test them electrically to verify the circuit integrity and verify the components actually operating. We can check them mechanically by looking at the current flow, which can verify the mechanical motion up and down in the case of a fuel injector, or round and round in the case of a fuel pump. And hydraulically, we can view the pressure change, pressure drop, and verify the state of flow in there. So on a conventional fuel pump, that is going to be a brushed DC motor. So we have the brushes and we have the commutators, and they have coils. So the magnets stay stationary, and then the coils spin inside one of these conventional brushed fuel pumps. It's going to look kind of like that. So the brushes are there, got the little motor down here. It's going to pump the, or it's going to suck up the fuel and then push it out the front, right? So a good test to do on this is going to be what we call a fuel pump current ramp test. So if you have a tool with guided component tests, it's already pre-built in there on the majority of vehicles. You're going to place the jaws around a wire somewhere in the fuel pump circuit. If you can get close to the pump, great. Otherwise, a jumper, take a fuse out, put a jumper in, or a fuel pump relay. Any of those will work. Somewhere in the circuit, around one wire in the circuit, and we want to see the current flowing through the commutator. So you can see how they're wearing by the current that they draw. So most automotive fuel pumps, some newer ones have more, but most automotive fuel pumps have 8 commutators. So in this case, we got 8 segments of commutator there, and there's a badly worn one. And we're going to see each of the bumps go across the screen. So we can see in this case, we get bumps going up and down. And each one of those represents one commutator. If we count out 8 bumps, since we know this in this particular one, it's 8 commutator segments. So if we count out 8 bumps, we get 1 revolution of the motor in there. Make sure they're fairly rounded. Make sure there aren't any missing. Let's just imagine in this case that this one was missing right there, and then the same one was missing right there. That could be one bad commutator. That could cause an intermittent no start. The one where you fix it by tapping on the bottom of the fuel tank, right? We can do a rough calculation of the RPM by counting a number of revolutions in a 10 millisecond window. So 1 revolution in 10 milliseconds is going to be 6,000 RPM. In this one, we see about 1.5. So that means it's roughly 9,000 RPM. So we can do the actual math by using the cursors on the previous screen. So the delta on those 2 cursors is 6.95 milliseconds. So 1 revolution of the pump takes 6.95 milliseconds. There's 60,000 milliseconds in a minute. So we take that 60,000 and divide by how long it takes for one time around, we get the revolutions per minute. So in this case, 8,633 RPM. So that is plenty fast. A good fuel pump is going to run 6,000 or greater. A fuel pump that is failing or worn or is weak is going to turn 3,000 or less. And if you get to 3,000 or less, you may have a drivability problem just because of fuel volume, low volume in the fuel. Right? Brushless fuel pump is going to work similarly but different. So it's basically opposite. So the magnets spin and the coils are stationary in this case. So we see a little animation here. It switches the polarity of the coils and the electromagnets to push those commutator segments, or these segments, these magnets around. That's what I'm trying to say. pushing the magnets around. So it's basically repelling the magnets as they go. So it switches polarity, positive and negative, depending on which way it needs to go. On this Camry we're looking at here, we have 4 wires to this control module. So we get the UV and the W legs, which are the 3 legs of the windings, and then ground, of course. So UV, W, and ground. And we can see it kind of looks like this. So this was on a UV and W, I suppose, and then we have the current clamp on this channel 1 here. So we can see it's flat, flat, and it switches. It goes negative and positive there, and then this goes positive, negative on the other side. So they flip back and forth. So you can see the current flow, no current flow when it's not doing anything. It's just 0. We get negative current down here, then it goes to nothing, and then we get positive current over here. So we can see how it kind of flips back and forth. You can also do an RPM calculation on this as well by putting putting your cursors in the front of one of those, and then at the front of the every other one type of look, right? So it's because it's got to flip positive and negative to do 1 full revolution. I have other videos on all of this information we're talking about too. We're kind of talking about this stuff high level today. If you want more information, there's plenty of other information out there on our channel. High pressure fuel pump runs off a camshaft. So if the camshaft's worn out, then that will cause an issue with a high pressure fuel pump if I happen to have a high pressure fuel pump on my vehicle. Which kind of works like this. Got a little spring in there, and it pushes up and increases the pressure coming out of the outlet there. This is especially for like direct injection vehicles. We'll definitely use this. Test the fuel injector as well. So as we said, we can check it electrically, mechanically, and hydraulically. So electrically would be the yellow line. So that's going to check this circuit itself and make sure it's working. The green would be current flow, and we can see it actually open right there, the little pintle bump. And then we can see the pressure drop a little bit, and then we see a pressure spike when it closes. So we'd be able to see all of that. So voltage, we would connect back probing at the harness. And when it grounds it, it's going to pull it down to ground. There we go. We got nice ground right there. We want to see it pull down nice and sharp to ground. And then when it closes, we're going to get another spike in there. And then that's this pintle bump right here is the actual point where it closes. Right, so we get a little excess electricity goes in there. We get a little spike, and then it closes. Current flow, same deal. When it opens, the current will ramp up. As it opens, we get a little bit less resistance at that point. So that is going to be where the pintle opens. So I want to keep an eye on that. If it's the same spot every time, then I know mechanically, internally, it should be working fairly well. If it's moving up and down, if it opens here, opens there, and being very erratic, maybe I got a bad spring in there. Just kind of bouncing around, right? We'd be able to see that. And then, of course, when it closes, no more current flow, so it goes back to 0. And then as far as pressure, in this case, the pressure didn't drop a ton on this particular vehicle, but you can see it dropping. Drops a little bit. And then when it does close, because it's closing and that fuel is flowing into the injector, when it closes, it has nowhere else to go, so we get a little bit of a pressure spike. And then it balances itself back out. So that covers us on fuel and a little bit of air, right? We can also test air using ignition, because you can tell whether it's rich or lean looking at the ignition system. This will verify that the ignition system is actually working, and it will also verify whether I'm rich or lean inside the cylinder if we do that. So here's an example of a cranking test at wide open throttle, just wide open throttle because this vehicle goes to fuel cut when you go wide open throttle, so that way that it won't start, right? We're just trying to see it cranking. So we see all of these are fairly even. That is good. If one was higher or lower, we know we'd have a problem, like in this example. So this is on a car. I was in the middle of giving it a tune-up, and guess which plug I had not replaced yet? I replaced these 3, and of course not that one. You can see how it's much taller, the spike there, because the plug was worn, so it had a much larger gap to cover. We can also look at the spark line and see what the condition is there. So we want to see it relatively flat like this. This is actually a textbook spark pattern. So we get the firing line, and then we get the spark lines fairly even. A little bit of turbulence in there, a couple little oscillations at the end. That's textbook right there. Now, what I did is I decided to cause a lean condition. I pinched off the fuel supply line, and when that happens, goes just fine at the beginning, and then it goes up at the end, which indicates a lean condition going up. Conversely from that, I can see a rich condition by it going down. Right? So that covers my fuel delivery, what my mixture looks like inside the cylinder, and whether or not my ignition system is working. So that's three P's in the pod. I have one more of those things that I need in order to make an engine run properly, and that is compression. A couple different ways we can check that. So one is relative compression. So that's looking at cylinders relative to each other, not actual numbers or values as to what's going on in the cylinder, but is this one a little bit lower, this one a little bit higher, sort of thing. So this is pretty clean. That's the way it's supposed to look. So 1, 2, 3, 4, 5, 6 cylinders on this engine. And then there is a number one injector, I guess. So we can see that it sprays a little bit before the top, but these are all fairly even. So that is a good running engine. Airflow is going through properly. We're using the starter to turn it over. We're looking at the current flowing through the starter. This is a vehicle that had a bad cat. So as we can see, every other cylinder is low. So it was on the odd side of the engine, and it just wasn't getting enough exhaust out. So it wasn't able to get enough other air in. So large pressure pulse 135 and a low vacuum pull, because that cat was clogged on that side of the vehicle. So you actually be able to see that it was tied to one bang. Now, if it was just one cylinder, then maybe you have a compression problem on just that one cylinder. But you can do all this. Don't have to take the engine apart to do it. You can just do a simple test with it cranking. If we find a problem cylinder, we could also do a running compression test to see what the problem may be inside that cylinder without having to take it apart. So this is using a pressure probe, and we can see this is a pretty standard looking running compression test. So we see the compression goes up, and then we have ignition, and then the compression goes down. Oops, back that up there. Compression goes down, get a little vacuum pocket. Then we go to exhaust, and we see the exhaust in there, and then we have our intake stroke, and we can see how it kind of changes there, and then the compression stroke again. So this is pretty textbook, the way it should look. If I have weak compression in a cylinder, we would see something along the lines of this. This is a vehicle that had poor compression in the cylinder, and we can see that barely makes it above 0 psi. So it's like wide open almost, right? Nothing going on there. This is the sister cylinder to this same vehicle, so we can see we have a nice high running spike right there versus the problem child, which it didn't barely make a spike at all. And then here's another example. This is one on that vehicle that had the clogged cat. So we can see that the exhaust pressure is ramping up. It actually goes above 0 psi, and on the exhaust stroke, you should not see anything above 0 psi because it should just be open out the back, yeah? So if I do see pressure building, then that means that exhaust is not making it out expeditiously as it should, right? So in this case, clogged cat. And then here's just kind of everybody all in one. So we have our running compression. We have current on fuel injectors. We can see where the fuel injector sprays, or actually no, that would be on, that's ignition, sorry. So that's ignition. And then this is the fuel injector there. So we can see the compression builds up right here, and spark fires a little bit before top dead center. And then we have the actual combustion process happening. So it goes down, we get the little vacuum pocket, then we go into exhaust again. Notice how this is a 4-cylinder vehicle. So I see 3 pressure pulses in there from the other cylinders. And then after my fuel injector sprays, which is right here in the middle, after my fuel injector sprays, right before the intake valves open, we can see how the look of the waveform kind of changes, because now I'm having turbulence come in, I have fuel come in. So we can see it looks a little bit different. We got some swirl going on, and comes down here into our vacuum pocket, and then once again, compression goes again, and it repeats. So I just thought that's kind of interesting. We can kind of bring it all together, and we can see everything on how this particular engine was running properly, right? All right, let's go live on the tool and take a look at a couple different things we can find on there that might help us in this back to basics journey we're taking. All right, so a couple things we can talk through here that would be related to what we were just talking about anyways. Pull up that BMW again. And if we go under engine, we'll see that like under fuel system, for example, you can go and under the fuel pump current ramp test. It's going to give you all that information that I just mentioned. Use a low amp probe. Go around one wire in the circuit, and then you're going to look at the commutators. You can also do a fuel pump RPM calculation. That's set in here as well. So it's going to tell you the 60,000 divided by how long it takes to turn, and that gives you your RPMs. Also in here, we have, oops, too far. So we also have fuel injector, of course. So we can go in and do a signature test, which is going to give us the electrical side of things. We can also do a current ramp test, which will give us that mechanical side of things that we talked about. There's a current ramp there. All right. And also in here, I'm going to get out of the vehicle, but once in the guided component test, under the classes, there's also, if you want to learn more information about pressure transducer, right? So 15-minute pressure transducer diagnostic class. It's going to be talking about in-cylinder pressure transducer testing. So you can see the different strokes in the cylinder and what's going on. Power stroke, exhaust stroke, intake stroke, compression stroke. And then you can see something like this. So connect the pressure transducer to the oscilloscope using the appropriate leads. To fit the pressure transducer, remove the spark plug from the cylinder to be tested. Use a suitable adapter to thread it in the spark plug well. Fit the spark plug in high tension lead or ignition coil. Connect the spark plug to a no good ground. So there we go. And then we would go through there and run this test. And you can see it running. Electrically disconnect the fuel injector from the cylinder being tested too, so you're not washing down the cylinder with fuel as you're doing that, right? So you don't want to damage your catalytic converter. That'd be a problem. So we'll walk through on that. Let's see. Let me pull that BMW back up there. Also on some vehicles, there is a compression test that you can do using actually ignition leads. So relative cranking compression secondary probe test leads. So for 6 or 8 cylinder engines, relative compression or cranking compression can be checked using regular supplied test leads and the special ignition presets that have been programmed into this test for the engine. So you're using regular leads with ignition. Battery starter motor must be in good condition for the tests. Battery yellow to positive, black to ground. Green optional hookup to cylinder 1 to get that. Spark plug wire inductive pickup as well. It's going to go, and you can go bring the time base down to 500 milliseconds on 3 and 4 cylinder engines. You'll be able to see that there. So it's going to look kind of like that. It's basically using the voltage drop on the battery when it cranks instead of using the current flowing through into the starter in order to do that. There's also some ignition tests in here. We were talking about doing that. So primary and secondary tests. So I can go in there and do a signature test on the primary side if I wanted to. There's a single fire and there's a multi-strike depending on the vehicle. In this case, this one does. Can go in a multi-strike at low RPMs and cooler temperatures. I can do a current ramp test on the ignition as well. So it's going to look very similar to the fuel injector current ramp, except it kind of goes up a little sharper. And then we see multi-strike right there as well. So a few different tests that we can do in that case. And then also, if you wanted to go in and do ignition tests using the scope, you could do that. There is a full ignition system testing apparatus in there on the scope. So couple different tests that we can do. Try and make it easy. Try and remember our basics, right? Don't forget the fuel, air, ignition, and compression when we're trying to diagnose a drivability problem, or maybe even a problem with a vehicle with a code, right? So it's just always got to remember those basics. So let's talk about what we're going to talk about next week. All right, so next week we are going back to our OEM-specific ADAS training, this time on Honda. So we're going to talk through how Honda kind of runs their ADAS versus how other manufacturers may do it a little bit differently. I know we've seen a lot of different looks between a few different manufacturers that we've done so far. So everybody kind of uses the same basic items, radars and cameras and stuff, but the way that they calibrate them could be a little bit different. So we're going to talk about some specific tasks on Honda next week. So join me. Same time as always, every Tuesday, 6 and 9 Eastern. If you want to join on Zoom, go to snapon.com/OT and sign up there. Otherwise, the 6 p.m. Eastern class goes to our YouTube channel, and the 9 p.m. Eastern class goes to our Facebook page. you want to see any of the other topics in this series, and like I said, we go way more in depth on each of those specific things in one of these other and many of these other classes, right? So we have different guided component testing. I know there's a few in there for um, uh, running compression and compression general use, ignition system testing, and so on and so forth. So if you want to see a little more information, a little more detail on that, you can for sure go to our YouTube channel, youtube.com/Snap-on Diagnostics. If you scan that QR code right there, that will bring you to the page and subscribe you automatically. Also, do we have your email address? If we don't have your email address, you may be missing out on things like technical focus articles, SureTrack blogs, quick tips, new product releases. They send out my training schedule periodically. So things like this timing chain diagnosis email, things like that. So if you want to receive those emails and you don't already, you can scan that QR code. It'll bring you to a little page where you can sign up and put your particulars in there, and then you'll start receiving those emails. All right, time for questions. And as I said, I am traveling this week, so this is pre-recorded. But if you do have any questions, feel free to email or reply to the Zoom email that you got on Zoom, or you can leave a comment on YouTube or Facebook, and I'll get to those when I get back. Also want to give you a reminder about my buddy Keith, who also does free diagnostics training. His is product-specific training. So Zeus and Zeus Plus is on Wednesday. Thursday is Triton and Apollo Tools. 7:30 p.m. Eastern. Go to snapon.com/OT to sign up for that. It is Zoom only. It's kind of designed to have the tool in front of you and you function through as Keith is functioning through the tool on his screen as well. And he goes through everything from soup to nuts, from starting to connecting the Wi-Fi, talk about security link, talk about Snap-on Cloud, all the way through fast track intelligent diagnostics. And then even in the back half, he talks about guided component tests and scope and meter functions. So definitely a very thorough class, worth your time if you want to learn more about your scan tool. And with that, I'd like to thank you very much for spending a little bit of time with me. Hopefully, I'll see you next week for ADOS. With that, enjoy the rest of your week. Enjoy your weekend. Have a nice night and take care.